Hello everyone, my name is Jordan and welcome to the first video in a series of video lectures regarding the methods for atomic spectroscopy. Now in this particular video, I will be focusing on the key concepts, theories, as well as the applications for atomic absorption spectroscopy. Now, the key concepts relating to the atomic absorption spectroscopy, or as it is abbreviated, AAS, is a quantitative analytical technique that measures the concentration of an element in a sample by measuring the amount of light absorbed by the atoms of that element. So AAS is based on the principle that atoms can absorb light at specific wavelengths that correspond to the energy differences between the electron energy levels. So this picture here shows an example of a setup for the atomic absorption spectroscopy. Now, when a sample containing the element of interest, so let's say lead, is exposed to light of a specific wavelength, the atoms of that element can absorb the light and be promoted to a higher energy level. Now, the atom, which has absorbed a specific amount of light, will the light absorbed by it is proportional to the concentration of the element in the sample. So this is an example of a hollow cathode lamp, which works specifically for lead. As you can see in the setup here, this is the hollow cathode lamp. Excuse me. So this HCl is an apparatus which is coated with the same element as the analyte, which functions to emit light as a light source to the nebulized liquid sample. So that is something we will go into later. Right, so the process of how this works is that firstly, the sample is prepared in a liquid solution. Then the liquid sample here is nebulized into a fine mist using a nebulizer. Then the mist of sample droplets is passed through a flame or an electrothermal atomizer to vaporize the solvent and atomize the unknown sample or a sample which is to be analyzed. So the atoms in the sample absorb light from a hollow cathode lamp. So for example, let's say lead at a specific wavelength, specific to the element being analyzed. Then in the detector, the amount of light absorbed is measured. So the absorbance is proportional to the concentration of the element in the sample. So when the absorbance is detected, that value represents the concentration of the element in a sample. So a more detailed explanation of the steps of AS. So first, the sample is prepared in a liquid solution before it can be analyzed by the AS. This can be done by dissolving the sample in a suitable solvent, such as water or acid. Then the sample solution, this is an important step, is that it should be clear and free of any suspended particles. Now next, the nebulizer. The nebulizer converts the liquid sample into a fine mist of droplets by So this is done by passing a stream of compressed air through the sample solution, and the mist of sample droplets is then passed through the atomizer. Now the atomizer converts the mist of sample droplets into a vapor of atoms. Now this can be done using a flame or an electrothermal atomizer. So in this case, a flame atomizer. A flame atomization is utilized. So after this is the light absorption. The atoms here present absorbs light from the halo cathode lamp at a wavelength specific to the element being analyzed. The hollow cathode lamp emits a narrow band of light at the characteristic wavelength of the element. Then the monochromator filters that light, whereby it goes into the detector, where the amount of light absorbed is measured by a detector. The absorbance is proportional to the concentration of the element in the sample. The absorbance is then compared to the absorbance of a series of standard solutions to determine the concentration of the element in the sample. So here is a more in-depth explanation of the previous statement. So the theory of AS is based on the Beer-Lambert law, which states that the amount of light absorbed by a sample is proportional to the concentration of the absorbing species, for example, lead, as we mentioned just now, and the path length of the light going through the sample. So an expression can be developed here, which is the Beer-Lambert's law, where the A represents the absorbance, C is the concentration of atomic vapor in the flame, and K is a specific coefficient to the element to be absorbed. So from the calibration curve of absorbance versus the concentration in the standard solution, the concentration of a sample in the solution can be determined. Now, AS instruments use a monochromator to select light of a specific wavelength and a detector to measure the amount of light absorbed by the sample. So this instrument is actually a component used to filter the specific wavelength of the light, the light from the flame. So then the absorbance of the sample is then compared to the absorbance of a series of standard solutions to determine the concentration of the element of interest in the sample. Now, AS is a technique widely used in a variety of industries. So samples from these industries include water, soil, food, beverages, and biological materials. The industries pertaining to the usage of this includes environmental monitoring, the food safety industry, as well as the clinical chemistry industry. Now, some examples of activities using the AS method includes measuring lead content in gasoline, arsenic content in drinking water, iron content in blood in the clinical industry, and measuring the calcium content in milk, as well as for environmental purposes, monitoring the copper content in the soil. So in this video, we have seen the key concepts theories as well as the applications related to AS. So that is going to be it for this video. I hope to see you again in the next video. Goodbye.